Hello, children. Today we are going to discuss numericals based on Chapter 7 Calorimetry. So, in this session, we will focus on exercise 11A and first 6 questions from that. Okay. Before moving into the details of numericals, I would like to reinforce the concept of principle of calorimetry. So, according to principle of calorimetry, we can say that heat energy lost by the hot body is equal to heat energy gained by the cold body. That means when a hot body is mixed with a cold body, heat energy will transfer. Correct? That means there is a transfer of heat energy. Heat energy passes from the hot substance to the cold one, right? So the transfer will take place till both the bodies attain the same temperature if no heat energy is lost to the surrounding. So keeping it very simple, principle of calorimetry says that heat energy lost by the hot body is equal to the heat energy gained by the cold body. So the important keyword from that, total heat lost from hot body equals total heat gained by cold body. Now, if we are coming into the mathematical form of principle of calorimetry, we can see that there is a formula m1c1 into t1 minus t equals m2c2 into t minus t2. Correct? This is the mathematical form. This is what we are going to use for solving numericals. So let us just see what is this m1c1 and this t1 minus t means. Okay. So if you have clear idea how to take this m, c and this t, you can easily solve the calorimetry based numericals. So I'm just making it very simple here. So when you're solving the numerical, you can always try just giving these ideas there, where the hot substance, we can make one column. You can write m for hot substance, specific heat capacity, and delta t for hot substance in one column, and in the second column you can write cold body. Then you can specify the mass, capacity, specific heat capacity, and temperature. Okay, so that easily you can get m1c1 and this delta t for hot body, and m2c2 delta T2 for cold body. You can easily substitute that into the formula. Okay, so let us see once again what is principle of calorimetry. So principle of calorimetry says that the total heat loss is equal to total heat gain. That means when there is a transfer of heat energy, when two substances are mixed together, there is a heat transfer. So what will happen there? One body will have a fall in temperature, that will be the hot body, and another will show a rise in temperature, that will be the cold body. That means there is heat loss from the hot body and heat is gained by the cold body. Now I'm just going to give the terms m1, c1 and t1 for the hot body. That means mass of the hot body is m1, specific heat capacity is c1, and temperature is t1 for the hot body. Whereas mass is m2 for the cold body, specific heat capacity is c2 for the cold body, and temperature is t2. Okay, so now we have m1 c1 t1 for hot body, m2 c2 and t2 for the cold body. Now if I mix these two substances, I will get a final mixture which will have a temperature that is just the letter T. Okay, this is T. I hope it is clear. Now here I said the hot body, there is a fall in temperature, right? So we will have delta T in our equation, that is Q equals mc delta T. Here delta T is indicating a change in temperature, so that change is fall in temperature for the hot body, correct? So the fall in temperature for the hot body will be T1 minus T. Okay, then for the cold body, there is a rise in temperature. So that is T minus T2. So for the hot body, delta T is equal to T1 minus T. Whereas for the cold body, delta T is equal to T minus T2. Okay. So now we can substitute that here. Okay. So according to principle of calorimetry, T total heat loss, that means Q equals this Q, correct? What is the heat loss, that amount Q here? That will be M1C1. Instead of delta T, we are writing this here. That's all. M1C1 into T1 minus T equals heat gain is M2C2 into T minus T2. That's all. Okay. So I hope it is clear now. This is the mathematical form of principle of calorimetry. Now children, we are considering only two sides now. That means one substance is undergoing a fall in temperature, other substances showing a rise in temperature. There is a fall in one side and there is a rise in other side. Now here we consider only the substances, right? So what if this is the mixture is actually taken in a container or a calorimeter or a vessel, the vessel also gains some heat energy, correct? The vessel or the calorimeter also acquires some heat energy, so we need to consider that part also. So let us just see that now. So if a calorimeter or a vessel is used for mixing the two substances A and B, we must take into account the heat energy gained by the calorimeter or vessel also. Okay, so just I am trying to demonstrate that now. If I have a hot substance, it is A, and a cold substance B, if I am mixing that, what will happen? Heat energy will be lost by the hot substance and heat energy will be gained by the cold substance, plus the vessel, right? The vessel also gains some heat energy. So here I'm just taking an example. Okay, substance A, in the sense it's a hot solid, and I'm mixing it with water. So what I'm going to write here, hot solid, okay, equals, this is the one which always lose heat energy. Okay, and water will gain heat energy, also the vessel also gain heat energy. That means in our equation, this is our normal equation, the normal format of principle of calorimetry, right? So in addition to that, we need to consider the part of vessel, that's all. Okay, that means we are getting a third part in this formula, that's all. First part, second, plus consider the third part, that is a vessel or the calorimeter, which also acquires some heat energy. Okay, so here what is this terms now? Hot solid will have mass m1, specific capacity c1, temperature t1, and water, that we can take as m2, c2 and t2 for water. Then vessel, that will be m3, c3 and t2. Look at this now, vessel and this water will have same temperature. That is a very important point. Okay, here the vessel and the water will have same temperature, so that you have to indicate in this final equation also. So as per the mathematical form, we can write the heat loss, that is this side, m1c1 into t1 minus t, it indicates a fall in temperature, equals, here there is a rise in temperature, that means heat energy is gained by these two parts. Okay, water and vessel. So this will be m2c2 t minus t2 plus m3c3 t minus t2, where you can see these are same temperature. Okay, so in order to make it comfortable or convenient for solving numericals, we can rearrange it again so that you can write it thus m2c2 plus m3c3 into t minus t2. So this will be our final formula. Okay, so if you are clear with these two types in principle of calorimetry, the first part and the second part, you can very easily solve the numericals based on this. Now one more simple formula is used in calorimetry, that is just related to power and heat. So we know that power is equal to work upon time, work done by time, that is W by T. So here we know that work is actually connected to energy, right? So sometimes it is equivalent, like work is equal to energy in many situations. So if I say this work is equal to energy, in the sense, according to this calorimetry discussion, the types of energy which we are dealing is heat energy. So I'm just writing W is equal to Q, that means Q is the heat energy. Okay, so here I'm just replacing this W by with the Q, where I'm just trying to say that, see, work is equal to this energy here, here the energy is heat energy, that's all. So P equals Q by T. Okay, I got another formula now, power, P equals Q by T, where Q is already a non expression for us. Q is mc delta T, so P equals mc delta T by T. Here children, please look at this delta T is the temperature and this T is the time. Okay, so P equals mc delta T upon time. Okay, so P equals Q by T, or Q is equal to P into T. So this is one equation, Q equals P into T. Let us start from question number 1. By imparting heat to a body, its temperature rises by 15 degrees Celsius. What is the corresponding rise in temperature on Kelvin scale? So the answer will be 15 Kelvin, because if temperature increased by 15 divisions on Celsius scale means corresponding rise would be same on Kelvin scale. Okay, so it should be noted that rise in Celsius scale is equal to rise in Kelvin scale. This is just because both the scales have 100 divisions and size of each division is same for both. So the answer, final answer will be 15 Kelvin. Moving into question number 2. Question number 2 has two subdivisions. First part is calculate the heat capacity. Calculate the heat capacity of copper vessel of mass 150 gram. So mass 150 gram, convert that here itself into SI unit. You got it. And here the specific heat capacity of copper is 410 joule per kg per Kelvin. These values are given and you are asked to find out what is heat capacity. Directly you can use this equation here, this equation, right? You are using that here. So you will get heat capacity equals mass into specific heat capacity. So direct substitution, you will get the value of heat capacity, that is 61.5 joule per Kelvin. You got the answer here. Correct. Second part, they are asking how much heat energy will be required to increase the temperature of the vessel in part A from 25 degrees Celsius to 35 degrees Celsius. So what you are going to find out? You are going to find out Q. Okay, so what is equation for Q, or the formula for Q? That is mc delta T. Check whether do you have M. Yes, M is already there. And do you have C value? Yes, it is already there, C value. What is not there? Delta T. But the information is there in the question. Delta T equals 35 minus 25, you will get 10 degrees Celsius. Now again direct substitution only, you will get Q as 615 joule. That's the heat energy Q. Okay, so that's about question number 2. Now we are going to discuss question number 3. The question is, a piece of iron of mass 2 kg has a heat capacity of 66 joule per Kelvin, and you are asked to find out the heat energy needed to warm it by 15 degrees Celsius. And in the second part, they are asking its specific capacity in SI unit. That's all. Okay, so let us see what are the given information. This is very important. You have to write it in your answer sheet. What are the given information in the question? So we have mass, that is 2 kg, and specific heat capacity is also given. Heat capacity is 966, that value is given, and delta T 15 degrees Celsius. We have these ideas. Okay, we have these values now. Okay, see children, for finding the first part answer, you can actually use the idea Q is mc delta T, that is known for us. Look at this first part, M into C. What is that? M into C, mass into the specific heat capacity. What it is actually? It is C dash, correct? Because we know this, C dash is equal to M into C. So I'm taking only this part now, M into C. So I'm just rewriting this equation as Q equals, this part I'm writing as C dash into delta T. Now let us apply that here. Q equals, C dash is 966, that's already there, into, you can just multiply delta T, that is 15. So you got the first part answer. See here, in all the questions you just have to apply that logic. Okay, we have basically 2 to 3 equations or formulas from this chapter. We are just changing that. Okay, yeah. In the now let us move into the second part. For that we are going to use again this relation, C dash is equal to M into C. From here we can take C will be equal to C dash by M. So C dash value is already there, 966, and mass is also available in the question itself. So direct substitution, you will get the answer as 483 joule per kg per Kelvin. Okay, it's an easy question. Okay, only in this first set we are just using this logic, that's all. Okay, so that's about question number 3. Now moving into question number 4. Question is, calculate the amount of heat energy required to raise the temperature of 100 gram of copper from 20 degrees Celsius to 70 degrees Celsius. Specific heat capacity of copper is 390. Okay, that's the question. So here mass is already given in grams. You can convert that into kilogram while you are writing the given information. And also you can write delta T. Delta T that you can write from the question itself. That means 70 minus 20, you will get 50 degrees Celsius. And C value is given, that is a specific capacity, that is 390. So these are the informations available directly. You can find out the amount of heat energy Q, calculate the amount of heat energy Q, in the sense you can use MC delta T. Mass is already there, then C value already given, delta T you got it. So it's a simple direct question. You will get 1950 joule here. Okay, that is solution 4. Now moving into question number 5. 1300 joule of heat energy is supplied to raise the temperature of 0.5 kg of lead from 20 degrees Celsius to 40 degrees Celsius. Calculate the specific heat capacity of lead. Again, specific heat capacity, that is what you are going to find out. So before moving into that, please write all the information like this. It is very, very important. You have to write, then write the basic formula. Then based on the question, you may please rearrange the equation. This is the format you need to follow for examination. Okay, so here let us see what is given. In the question it is given Q as 1300 joule already given, M is given 0.5 kg, delta T you can write it like 40 minus 20, 20 degrees Celsius, and only C is not there, right? That you can easily find out from this equation. Q equals MC delta T. Take C outside, okay, and substitute all the values here. Take C out, you can actually directly substitute these values. You will get answer as 130 joule per kg per Kelvin. Direct question. Now the final question of this session, okay, solution 6. Okay, so question 6 is, find the time taken by a 500 watt heater to raise the temperature of 50 kg of material of specific heat capacity 960 joule per kg per Kelvin from 18 degrees Celsius to 38 degrees Celsius. Assume that all the heat energy supplied by heater is given to the material. So this question is little different from the previous ones. Here we are going to use the equation what I mentioned as power and heat related formula, right? So that concept we are bringing here. Okay, so let us see what are the given information. Power is given 500 watts. M is given, already it is given, right? 50 kg. C value is given, correct? C is given in the question, specific capacity 960. That value is already given. Delta T also you can write 38 minus 18, 20 degrees Celsius. So you have these set of values. Okay, you have these set of values. Okay, so in this point you may please try to remember the concept power is equal to work by time, and also you can rewrite that power as Q by T, where Q is MC delta T by T. I already told you this delta T stands for temperature and this is for time. So I'm taking this now. Okay, power equals MC delta T by T. Okay, because here we are going to find out time, right? Only with this concept we cannot find out that, right? So we are utilizing this equation, P equals MC delta T by T. Okay, substitute all the values. P value is 500, M is already there, C value is already there, delta T already you have 20, divided by T. So what is unknown, take it outside. T equals, just rearrange this equation in this way, you will get the answer in second. It is okay, you can write in second also, 1920 seconds, which is equal to 32 minutes. Okay, so you know the conversion, right? Conversion is already given here, so you will get the answer as 32 minutes. See children, this is what I said, you have question related to this power. Okay, where you are just simply using this formula, so please make a note of this. Okay, so in the next video we can finish the remaining questions, like question number 7 to 13. Okay, please practice these questions, please work out these questions in your classwork, okay, before the next video comes. Okay, so in the next video we will finish the first set of exercise 11A. Okay, thank you children.